Hello. Uh, this is my first time leading the dynamics class. So Tim timed this perfectly with the quarantine or whatever we're calling this now. Um, so I am going to talk about chapter 16 today, parts 1 through 3. Generally, my hope is to kind of keep this more or less the way that Tim had it. I may have to adjust some things just because the sort of delivery is a bit different. Um, in particular, I think in person, I think I want to save some of the activities for in person. So I'm going to go through the main slides in these videos and maybe the individual problem, but I think I want to save the final quiz and also maybe the group project or group problem for when we discuss face-to-face. And I have some other examples I've kind of worked up to go through there as well, so we won't run out of material. But on the whole, it should be similar to what Tim has been doing. All right, so chapter 16 is on the planar kinematics of a rigid body. So the goal for today is to kind of, first off, just break down motions and figure out whether something has translational motion or rotational motion. And it's not always obvious, just, you have to think about it. And then we're going to start breaking down these motions and try to solve some problems. Okay. Usual sort of outline. Oops, sorry. Okay, so hopefully you've done the reading for the start of chapter 16. So there's a reading quiz. Question 1, if a rigid body is in translation only, the velocity at points A and B on the rigid body are blank. Well, now if you think about it, so A is, they're different, C is depend on their position, D depends on the relative position, and B is always the same. Well, if D or C are true, then A, C, and D are also going to be true. So B is the odd one out. So that's got to be the right answer, and that's true. So if objects have translational motion, they will have the same velocity. All points on the body will have the same velocity. Question 2, if a rigid body is rotating with a constant angular velocity about a fixed axis, then the velocity vector at point P, some point in the body, is blank. Well, you know it can't be D because A and B are manifestly different. So they would only be true if A and B are only the same if it's 0. The answer is A is the right expression. All right, so we're going to be talking about objects which are moving around and possibly rotating or possibly not rotating, and it can be sometimes a little tricky. So for example, here you have these people sitting in a car. Hopefully they're 6 feet apart. I can't tell. And it's an amusement park ride. So it's going around, but notice what they're doing. They're going around, but they are maintaining a level path. So if you were sitting at the back of the bus, you wouldn't think that the driver at the front of the bus is moving. So it turns out that's what's called a curvilinear translation, not a rotation. And one way to say that is there is, in fact, the fact that if you're sitting at the back of the bus, the driver doesn't look like they're moving. So they look like they're at a constant position. Okay, so think about that now. They're going around in circles, so every passenger does feel an acceleration. The question is, do they feel different accelerations or the same acceleration? Well, let's come back to that one. We'll answer that in our discussions. Okay, and then other beyond amusement park rides, these concepts have all sorts of applications for machines. So gears, pulley, cams. Cams are objects which rotate, but because of usually some sort of off-centered character, as they rotate, they can be used to drive horizontal motions. Or I should say just translational motions. Right, so all these components are rigid objects, hopefully. And so they fall under the purview of this chapter. So we need to develop general tools that allow us to analyze motions of rigid objects which rotate, because it comes up a lot. All right, so types of rigid motion. Obviously, rigid objects. So think frozen pizza, not pizza dough. So we're not talking about something that can stretch or elongate. The objects themselves are rigid. Take them to be made of metal if you want. And furthermore, we will limit ourselves to rotations in a plane, in a 2D slice. We won't talk about here things like a top as it spins and precesses and wobbles. That's a more complicated problem, much more complicated problem. All right, so there are three, well, you might be counting, say I see 4 pictures, and I guess, well, they're going to say that the top 2 are actually the same, in the same family. Anyways, they're really different, so you should know the difference. All right, so we have 4 basic pictures here which capture everything. One is called rectilinear translation. So that's where objects move side to side or up or down, or kind of straight line motion. And you'll notice that yes, each point is moving in figure 1 on the top left, but if you were sitting at one of the dots, say here, if you were kind of located at the bottom and you were looking at the dot in front of you, as you moved, the dot in front of you moved equal amounts. And so you guys always, it would look like it was at a fixed position relative to you. So if you were here located at the bottom, the dot at the top would look like it's fixed and not moving. So that's called rectilinear translation. So here we kind of have the analog where we let it start to bend. This is called curvilinear translation. Notice if you're standing right here at the lower dot, at all points along this arc, the upper dot looks like it has a fixed relative position relative to you. So both of these are translations, it turns out. So it's kind of like you riding along in a bus. I suppose this is a bus sliding straight sideways, and this is a bus that is spinning. But in either bus, hopefully, you are seated in your chair and your bus driver's in the front of the bus, and relative to you, the bus driver isn't moving, isn't having a change in position. So those are both translations. Down here, we have another type of motion, which is called a rotation about a fixed axis. Okay, that just means there's a constant axis or a line, and about that line, every point in the body traces out a circular trajectory or path. And that line passes right through the centers of those circles. So that's a rotation. And then a general planar motion is a combination thereof. Okay, so this slide really is just saying what I said. if a translation occurs when every line segment on the body remains parallel to its original direction during its motion. When all the points move along straight lines, then it's rectilinear. Otherwise, it's called curvilinear. Rotation is about a fixed axis. Here you go, keyword, key thing, circular paths. Okay, circular, if every point goes around a circular path centered on a common axis, then we call this a rotation about a fixed axis. And then a general motion is a mix of the two. Okay, so here's a kind of a typical sort of application we have in mind. We have some sort of a machine, and the slider goes back and forth. We have a wheel which rotates, and then there's an arm here which also rotates. And you'll notice that this arm has the same length as the radius of the wheel. And then as these objects spin, one thing you notice is that this horizontal bar will be carried around with it, but because the two, it's the same radius on the vertical bar and the wheel, you'll notice that this horizontal arm remains level to the ground all the way around. So in fact, that means if you were kind of at the back side of this arm, looking at the front side of this arm, you wouldn't say that that front point is moving at all relative to you. This is a curvilinear translation. It's curvilinear because the motion does have curvature, but the relative positions do not move all along that rod. Contrast that with general planar motion. So this diagonal bar is going to have a twisting motion as it moves in and out. So that's a more complicated motion. And it's a general planar motion. You can tell these devices can get quite complicated once you put them all together. So you just have to go slow, think it through, and focus on one piece at a time, and then glue the information together. Sorry about that. Crisis averted upstairs. All right, so let's focus on translational motion. So here we have sort of a general picture. There's a rigid object, and there are 2 points marked on it. And if you look at that object, there's a point A and a point B, and they have different position vectors relative to some fixed coordinate system, which you could imagine is on the ground or something rigid, not moving. And then, but if you were standing at A, looking at B, then if you have a translational motion, that vector, that relative vector, RAB, is constant. It's not changing in time. Okay, so that doesn't mean that A and B aren't moving. It means that relative to each other, they aren't moving. So that's the hallmark that's really the definition of translations. All right. I don't know if you guys can hear all that, but apparently it's very difficult to go across the living room floor. So if we want to compare velocities, as usual, we would take a derivative of the position vectors. And when we do that, because the relative vector is constant, when we take derivatives, you're going to get a 0 there, which allows you to immediately conclude that when you have translational motion, all points in the object have the same velocity. Okay, so that's kind of a nice thing to be able to just state. For any shape undergoing translational motion, they have the same velocity. Then, by the same logic, if you can take one derivative, you can take two, and then the accelerations would be the same too. So for translational motion, all objects in the body have the same velocity and the same acceleration. Okay. What about rotations? Now this one's, so they've given us a nice little picture here. Yeah, so to do this, what you want to do is you want to kind of grab your hand, let your hand curl around with the rotating object, and your thumb is going to point in the direction of the axis of rotation. And all right, so omega is going to point along that axis. And so that's a little bit funny. And so omega points along that axis. And so it's kind of a weird deal. We're used to drawing omega a lot of times in physics 1 as like with a little arrow that arcs, kind of a little bend. But it's actually, you can think of it as a vector, and it points along the axis of rotation. All right. But the definitions are basically the same as we had in physics 1. Omega is the derivative, the scalar quantity omega, or the number omega, is the derivative of the angle with respect to time. And we're going to say positive is counterclockwise. And angular acceleration is the second time derivative of the number representing the angle. And again, positives are defined in the usual math definitions. There's a nice little formula that you get. Basically, it's just the same way where, here, I'll show you. Switch screens here. Okay, so just like for velocities, we had velocity dv equals a times dx. Well, for rotations, we're going to have omega d omega equals alpha d theta, or a handy little formula there is then alpha equals omega d omega over d theta. Okay, so that's a little formula that might be useful to you. All right, so that's what we have down here. We have, this is just the usual definition of alpha, is the second derivative with respect to time. And then, well, really that comes from L'Hopital's rule, is where that, what we really did. But anyways, okay. All right, and as we had in physics 1, you can work out kinematic equations. If alpha is constant, then the algebra is simple, and you get what we used to call rotational kinematic equation 1, which says that that omega changes linearly in time. The change in theta, change in angle, varies quadratically in time, and rotational kinematic equation 3, we called it, which just relates the angular velocity squared to alpha and the change in theta. Those are only true when alpha is constant. Okay, so they're very similar to what you had for rectilinear motion. These are exactly the same. You just remember in physics 1, I always said you could just start with your normal kinematic equations and just switch from Latin to Greek letters, and just there's a one-to-one dictionary between these equations, between rectilinear motions of a point particle and then the angular equations for the rotational problems. All right. Right. So this one is a little bit, maybe a little bit more complicated. The velocity of a point on the axis of rotation Um, well, let's see. In physics 1, we called it R omega, but now we can be a little bit more sophisticated because, let me switch that out here. So in physics 1, we simply said that the tangent, oh, sorry, hand got in the way, that the tangential speed, we said that v, tangent to the circle, was equal to r times omega. And that's the equation we had in physics 1. But now we can be a little bit more sophisticated. I want to think about, so I have an object, a particle, which is rotating. So we know that the velocity at this point points that way. And if you're thinking about it, you want to take your hand and curl your hand around with it. And what you would want to say then is that the angular velocity as a vector quantity equals the number omega times the vector which goes into your eye. So sometimes I draw that as like an arrow dot shooting you in the eye. Okay. And on the other hand, if I'm marking this point here, change colors. Okay, for this point here, then the position vector of that point is in green. I'll call that R. So if you think about that, what we had here from physics 1 is really true for the magnitude of this. Okay, that's going to be true for magnitudes. If we want to turn it into a vector equation, we have to get everything oriented the right way. So if you think about it, let's work out which way would omega vector cross our vector point. Which way would that point? So omega vector is into your eye, and r vector, oh dear. So r vector, struggling to see it as you guys would see it. Let's see. Well, I'll do it as I see it. So into my eye is what I'm saying. All right. So r vector, so omega is going into my eye, and then I want to curl my fingers towards r, and then I get something which points upwards. I think that works out the right way. So this is what I'm seeing. Okay. So it's as I look at the screen and I look at my hand and I poke myself in the eye. Sam would really like that. I can tell. She's always out to get me. So into my eye, curl my fingers, thumb goes up. So what I see is to get the direction of all these things to hang together, then in fact, the velocity has to be omega cross r. Remember way back in the first slide in the little quiz, they had one of the options being r cross omega. That would give you minus the velocity. Okay, so this is the velocity of a point on the rigid rotating object. Okay. Okay, so that's the origin of that formula. Okay, no surprise. The acceleration can have both a normal and a tangential component. The normal component is the centripetal acceleration, and then the tangential component is what you get, it's the acceleration along the edge of the circle. It's, what torques would produce if you want. Um, okay, no big surprise there. Okay, so let's go through this. I wrote them all down, but I thought I would go through it on the other screen. You can kind of see where the various quantities come and how they're interpreted. Um, so, so I gave you the formula for velocity for rigid rotation. Let's work out acceleration. All right, so let me switch back. And there we go. Okay, so going on to the next page, and it only seems like I'm going to just make this stuff up as I go. But in reality, I did plan. It's a special skill to take something and prepare for something and present it in a way that makes it look as if you just made it up. That's some sort of ability. Okay, so all right. I actually worked this out for kind of a well. So let's kind of imagine the following situation. Hopefully, I can make this seem a little bit more, kind of explain where these formulas come from a little bit. Detailed, yes. All right, so let me try to. All right, so I'm going to draw a picture here. I apologize. So what we're going to have, let's imagine it is 3D here. So I have Z, X, and Y. And then what I'm going to do, I'm going to imagine I've got some random shape here, some random object. And I'm going to imagine there's some axis of rotation. Oh, I have to change tools here, I think. Change color. So I'm going to have an axis of rotation. I'm going to put that in red. Boy, there you go. Okay, so this is my axis of rotation in red. And then I'm going to mark a point. Doesn't matter which point, because remember the relative velocities between any 2 points on this rigid. Well, shouldn't say it that way. Instead, I'm just going to pick a point, and then you can work this out for any point. We'll write it in terms of general R, and go from there. So I'm going to mark this point because it's the least cluttered point in the diagram. I'm going to call this, oh, it doesn't really matter what I call it. Okay, so there you go. And this point here, this whole object is going to follow a path around the axis of rotation. So I'm going to imagine that every point swings around. But in particular, this point is going to swing around like that. Okay, so that's kind of the idea. Every point is going to swing around the axis of rotation. And I'm going to go ahead and draw a line from the origin out to that point. Okay, and I'll put in green the radius that point would experience. Okay, so that point experiences a radius in green. Okay, and I'm going to call that radius rho. I guess that's what I'm calling that letter. How would I not do that? Sorry, it's not as fancy as Tim's. I know. All right, so I'll have the radius. I'm going to erase this a little bit. And I'm going to say that the radius is rho, okay? And that's fine. And I'm going to call this point, I'm going to call this point A. A is the point. And I'm going to call this R sub A. Oh dear. I'm writing this on an iPad, and it doesn't help that my kids have dropped it, and it's got about 5 breaks across the screen. R sub A. So rho is the radius of the point A, and R sub A is the position vector of the point A relative to the origin. And finally, because this diagram is not complicated enough, I want to mark out an angle. I want to mark out an angle, and the angle I'm going to call Greek letter phi. Greek letter scribble, more like. Okay, Greek letter phi gives me the angle. Okay, so that's the idea. So the object is rotating around. So here's the red axis. The object is, say my pen, is rotating around like that. And the angle that the rotation makes, the angle between the line of the axis of rotation and, if you want the, I guess it's kind of, it was like a cone being swept out by this RA vector as it moves around. That angle we're going to call phi. It looks so much better on my on the paper. I don't know if I can do this. It'll probably, well, okay, I can't do much about it. All right, now, if you grab it, your hand, and curl your fingers around with the axis of rotation, we would see that, in fact, omega vector points along the red axis there. Okay, so it was parallel like that. All right, so that's the situation I want to analyze. Okay, so now, remember, rho is the radius associated with the circle that the point travels along. Okay, so I want to kind of draw a blown up version of that, just focusing on the stuff that matters. So I've got my axis of rotation. I did that in red, I think. So I'll let me try a slightly larger one. Axis of rotation, and I'm going to have a circular path that goes around it, and I have omega going that way. And I'm going to have, here's a point, I'm going to have RA and rho, okay? And then I have angle phi right there. Okay, so if I think about that, well, I know that the I know that I can think about the magnitude of the velocity at A. Well, that's just going to be the derivative of the arc length dt. And since it's on a circular path, I know the arc length is going to be related to theta, the angle around the axis of rotation. So I can write that as rho times d theta dt, like we've done in physics 1, or rho times omega. Okay? And then, if I look at rho, And I see rho is here. It's on the side, there's a triangle here, okay? So rho is opposite phi. So I can rewrite this and say that the speed, omega, sorry, not speed, not omega, sorry. The speed is equal to rho times, oh, sorry, not rho. It's equal to okay, so I can, instead of using rho, I can write that as the magnitude of RA times the sine of phi. Okay, so that's good. Well, that's kind of nice because then that lets me at least say that this equals the magnitude of omega cross R, A. Okay, but that still doesn't let me know whether it's omega cross RA or RA cross omega. So to do that, we're going to have to work just a little bit harder. Well, actually, I'm just going to do it the same way I did it before. So then by looking at the way my hands go, omega cross rho would point in the right direction. So it in fact has to be VA equals omega cross RA. Okay, so there's that one. Now let's work out the acceleration of that point. That should simply be the time derivative on the velocity. Which, if you think about it, that's simply going to be omega vector dot cross RA. Oh, I see my hands dragging on the iPad. RA plus omega cross RA dot. So I'm just using the product rule using inside the cross product. All right, well, that's nice. That just gives me alpha vector cross RA and plus, RA dot is just the velocity vector. So that's going to be omega cross the velocity, which is omega cross RA. Wait, I have to move this down to a new line. So that'll just be omega cross RA. So it's a cross product of a cross product. Whew. Okay, now how do we interpret these two terms? Well, alpha, if we go back, I should have said this, alpha points along the axis of rotation. So just like omega cross RA is tangent to the circle, alpha cross RA is also tangent. Tangent to the path of this point, so it's along the circle. And then I have to work out this way. Which way does this point? So this one, if you think about it, so it's omega cross RA. Okay, so first off, let's do the quantity in parentheses. So I want omega cross RA. So if you think about it, omega cross RA, that's going to be tangent to the circle, along with, parallel to the velocity vector. And then I have to do omega cross the direction of the velocity vector. So that's going to be omega cross that. So if I'm looking at the diagram here, I have omega. I'm going to curl my fingers in the direction of the velocity vector, and that's going to point towards the center of the circle. So in fact, the second term points radially, or the book likes to call this the normal direction. Okay. But in physics 1, I called it the radial direction more. Same thing. All right, so that's kind of so I mean, we can do the cross product, but it's a little bit tricky to see. So you just have to go through and think about it. There's an identity, and I don't know if you guys did this in Calc 3, so I thought I would derive it. It comes up. It's one of these things that you should, when you have cross products, there are some unusual relationships between things that you may not know or may not just be obvious. I don't expect you just to memorize them, and every time I go to do them, I have to kind of think about it. So I wouldn't, I don't know that it's worth memorizing all of these because there are several weird ones. I'm just giving you one. But you should know that cross products have equivalent ways to be written. Just a second here. Okay. Oh, there it is. All right. So this identity is a little bit weird. So I'm going to write the answer down, and I'm going to try to show where this comes from. So the statement is the following. Omega cross the quantity omega cross R equals omega times omega dot R.
Dad, are you ever going to come into my room?
Okay, so so we have the following relationship that we're trying to show, that omega cross the quantity omega cross R equals omega times omega. I should put my little vector symbols here. Omega vector. I have omega dot R vector minus R times omega dot omega. Some people write omega squared. Okay, so where would that come from? Okay, so this one's a little tricky to think about. So what I did was say this in a clever way or in a good way. So what I did was I wrote I kind of thought about this part right here, and I worked out the magnitude of it. So let me start with a better picture. Um, so I have like this, and here's my angle phi. And what I have is along the component perpendicular to my axis of rotation is going to have a magnitude of, so this side of the triangle would be omega squared r sine phi. Okay, so that's omega squared r sine phi. And that's just coming from the definition of the cross product. So I'm working out the magnitude, the magnitude of omega cross r equals omega squared r sine phi. And so that would live along the perpendicular component. All right. And then well, okay, this is opposite phi, so I immediately see how to work out the adjacent side. The adjacent side would be omega squared r cos phi, and then on the hypotenuse you would have omega squared r on the hypotenuse. All right, now, so what I'm basically going to do, we've already argued that this triple product is points in the radial direction. And what we're going to do is write the radial direction as a piece which is parallel to r, and then another piece which is parallel to omega, is the idea. So, which would be along the axis of rotation. So the part along the axis of rotation, so this side would be parallel to omega vector because it's along the axis of rotation. And I see, okay, well, it's parallel to omega and it has an omega, so I can write this as this part of the vector would be omega hat, the direction of omega, times omega r cos phi. And that is nothing other than omega vector times omega dot r. Okay, so that's this portion right here along that gives you this side. And then I have to write this one as a vector. Well, clearly it's along the radial vector. So I can write it as I can write it in terms of, oh dear. So the other side was, so I had a triangle, and on this side I had r omega squared along parallel to the r vector, so I know that I'm going to get r vector times omega squared, but that's nothing other than r vector times omega dot omega. Okay, so what I want to see then is that I can write, or what I'm starting to build up is I can write this horizontal piece along the radius of the circle as a sum of something in the omega direction and something in the radial direction. And The only thing that's left is to get the minus signs right. So let's see here. So what I want to say is, if I put in the arrows, I should have a vector here like that, and this other vector would be like that, and then this vector. And so what I want to do is think of this horizontal piece as a vertical piece plus a negative diagonal piece, all of which, so I can think of it then as, so basically I say this equals this plus that. So that tells me, working them all out, that omega cross r equals omega times omega dot r minus r times omega squared, as claimed in the notes. Okay, so you'll see, in fact, the formulas I was just writing down, that you had a radial and a tangential portion are in fact right there. And they've used the result that we had, that I derived, and simplifying it down to 2D. So if you're in 2 dimensions, there's a simplification that occurs. Specifically, in 2 dimensions, omega and r vector are going to be perpendicular, because omega, if you're rotating in 2 dimensions, omega will point in the 3rd dimension, which is actually out of the plane. So omega is going to be perpendicular to any vector which lives in the plane. So this term will give 0 in 2D. So just in 2D, this formula simplifies to only be this term, the last term. So the final result I get for 2-dimensional acceleration, or for rotations in a plane, will be the following. I can never get there. So I'm going to finally end up with the acceleration being alpha, go back here, just so you can see where it came from, alpha cross r, that's the tangential part, minus r omega squared. Okay, so that's, or if you're just writing out components, well, okay, so that would be, this will be the tangent portion, and this will be the normal, or I usually call it radial. Okay, so that's where those come from. All right, and as usual, you have 2 orthogonal components. You can work out the magnitude of the acceleration, Pythagorean theorem. It's pretty standard stuff. All right. So when you have a rotation about a fixed axis, sort of a general procedure they give, you want to fix a sign convention, use your hand to pin that down. I usually try to go with the standard math sign convention so I don't have to think about it. And what a typical problem is going to be is you're going to be given, say, some object which rotates with a known frequency. It could be constant or it could be variable, but it'll be known. And you're going to want to try to translate that into some sort of statement about maybe a linear variable or some other quantity. And so what you want to do is come up with some relationship relating two things, maybe some sort of geometry problem. And once you get your general formula, and you have to write it all in sort of abstract, symbolic notation, then take a time derivative, and that gives you the relationships between angular velocities and velocities or anything like that. And then finally, if you need to define the accelerations, you can pull it all together with vector properties. Okay? So that's generally the method to solving one of these problems. Here's an example. I want to go through this example with you, and then we'll do the group through here. Right. Then we'll go through the concept question and the group stuff live. Okay, so take a look at this picture here. Okay, so you've got two gears. They're intertwined, okay, so they don't slip relative to each other. And they have different radii. Circle A has a radius of 75 millimeters. Then the larger gear, B, has a radius of 225 millimeters. And then B has a smaller circle welded onto it of radius 125 millimeters. And on that, labeled by D, and wrapping around that is a rope that's going to pull up a bucket or whatever that is. And you have to squint here. The first time I did this problem, I didn't squint closely enough. So if I look really close, I can see that there's a gray arrow inside, or right next to the gear A, telling me that it's rotating clockwise. So that's the that is the angular acceleration for A. And they give me the number is 4.5 radians per second squared. So what they want me to do is to find the velocity of cylinder C and then the distance it travels in 3 seconds. As I look at my notes, I only did the velocity. So we'll have to figure out the distance here as we go. All right, so we want the velocity of point C at time 3 seconds. Okay, so to do this, I'm going to start with the following observation. The observation is that these 2 points can't move, can't slip relative to each other. So that means that basically the arc length traveled by one has to be the same as the arc length traveled by another. The only caveat being that if one object rotates in a clockwise fashion, the other object is going to, it goes in a clockwise fashion, which is going to make the other one go in a counterclockwise fashion. Okay, so there's a minus sign issue there. All right, and so that's what we want. We want to use the fact that the arc length traveled is the same for both to get a relationship between the different angular quantities, and then the rest of it's pretty simple. Okay, so let's switch over and I'll try to solve that problem. Oh. All right, here we go. Piece of paper down so I don't track my palm on the pad. I have a circle A, and I have another circle, B, and then centered on the same point, I have a circle D. And then I have the bucket, or whatever that is, point C down there. Very good. Now, I have various numbers here. So I know that the radius of A equals 75 millimeters. The radius of B equals 225 millimeters. And the radius of D equals 125 millimeters. All right. And then I know, similarly, that alpha for A is 4.5 radians per second squared. Now, I'm going to use math convention. So I'm going to say that because it's rotating in a clockwise fashion, I'm going to say that's a negative alpha. Okay? Well, all right. Because I know the arc length traveled around A, A is the same as it is for B, that tells me, in order for that to be true, I know that RA times omega A must equal, a little space there, RB times omega B. That just ensures that the distances traveled are the same. However, one of the omega for A, it starts from rest. I should have said that. It starts from rest. So I should put that up here. Omega not equals 0. So if omega, with time, omega starts to rotate in a clockwise fashion. So I'm going to say that's negative. Therefore, B is positive. So I need a minus sign in there. Okay, so that's just to get my conventions all fixed. Okay, so that's one thing. But because D is welded onto B, that means they have the same omega, so I can write that as minus RB omega D. That's useful. And then finally, since I actually want the velocity of the bucket, what I know is that the velocity of the bucket has to be the same as the velocity, the tangential velocity along the circle D around the rim. So I know that the velocity at C equals R times omega D. Okay, so now to solve for the velocity, I'm going to just string these all together. So I'm going to get that the velocity at C equals omega D times the radius at D oh dear. Yeah, that's right. I want to go back. Sorry. Erase that. Wrote the wrong thing here. I want to write that as RD times omega D, but I can relate omega D from up here. I can write omega sub D. I can relate that to omega sub A with some other little factors. So I get minus RA over RB times omega A. Okay, so if I can find omega A, I'm done. So I get the velocity of C equals minus RD RA over RB times omega A. But because alpha is constant, I can use the rotational versions of kinematic equations like we would have done in physics 1. And I can say that omega A is nothing other than alpha A times the time plus the initial angular velocity. But since it started at rest, this is just 0. And so the formula I get for the velocity is minus RD RA over RB times alpha A times the time. And I suppose, okay, so then we can plug in numbers here. And if I do that, when I plug in numbers, at time equals 3 seconds, I get negative 562.5 millimeters per second. All right. Similarly, well, once I know the formula for the velocity, I can find the vertical displacement by integrating it again, and I can get delta y equals the integral of the velocity dt. That's just going to be minus RD RA okay, times alpha over RB times the time squared over 2. And I don't have a calculator right here with me, but that should be the formula. All I did was, once I had the formula for the velocity up above, I just integrated it again to find the change in position. Okay, so let's see how we fared. And they did their algebra a little differently than me. Oh, you know what? I had a minus sign problem. Apologize. Alpha should have been negative. Alpha A should have been negative. So I should have had, put that in red. This should have been negative. So the 2 minus sign should have made this positive. And that's exactly what they have. Positive 563 upwards. Okay. And I didn't type it in, but I assume that you get the same answer from this, from the equation I gave for the vertical displacement. Okay, so that's what I want to do in this video. In class, we will work through the quizzes and also the other examples. All right, see you guys.